So we finished our analysis of ideal gas cycles, but now a couple of subtle points to discuss. Now we've been drawing traces in the PV plane, and this assumes that, you know, each of these points has a well-defined pressure and volume. And the internal energy would depend on what that pressure and volume are, because it's what we call a state function. So it depends on the state of the system. It depends on the state of the system being well defined. Now, because it depends on the state of the system, if you start at this point and then return any way to that point, then the system should be in exactly the same state. So for a full cycle, there should be no change in internal energy. Now, there is work done and there's heat flow, and both of those depend on the area of the loop. And for instance, if work was out, then heat would be in, and that would be, say, like an engine. Alternatively, if work was in and heat was out, then that could be perhaps an air conditioner or a refrigerator. Now, when we draw points like that in the PV plane, we're assuming that there actually is a pressure, only one value of pressure, that's uniform throughout the sample. In order for that to be true, it turns out that things have to be changing fairly slowly. We have to be at equilibrium or very close to it. Let's imagine, for instance, that we have, say, a metal box and there's some gas inside. And let's say that we heat it up with, a flame, okay? So burning hot flame here. Now, that side's going to get hot then. Actually, we'll draw the heat down here, okay? And so this side's going to get hot. And then the gas molecules inside, though, the only way that they're going to get hot is by, first of all, collisions of gas molecules with this wall. Now, inside this steel wall, this metal wall, those atoms and molecules will be vibrating more quickly because of the heat. So in the collision, there'll be some energy transfer. So after gas molecules collide with the hot wall, they're going to be going faster. But of course, that just affects the gas molecules right down here. That increase in internal energy that is coming from this hot flame, that's going to have to get transferred through the whole gas. But the only way that that happens is when these now moving much faster molecules collide with other ones. And that makes them go faster. And then they collide in turn with other ones, and they go faster, and so on and so on. So that thermal energy makes its way from this hot surface throughout the entire gas. So that's what it says right here. Now, in a similar manner, if you were to suddenly push on a frictionless piston, then you would have an increase in pressure right next to the piston. You would sort of pile the gas molecules up next to each other. And it would take time for that push to sort of be transferred, because the atoms and molecules would then sort of collide and push with their neighbors, and they would collide and push with their neighbors, and so on and so on and so on. And it would take a while for that increase in pressure to be transferred throughout the entire gas. So pressure, volume, and temperature are only defined when we're at or very close to equilibrium, and if changes are made very slowly to the system. So one way that you might do that is if you, say, had gas in a cylinder, and if you very slowly added pebbles, sort of one at a time, to the top surface. And so that would, by just making a tiny change and giving it time to equilibrate again, you would be staying close enough to equilibrium that you could say that the pressure, volume, and temperature were defined all the way through this compression. Now there's a word for that. Slow changes, when we're staying close to equilibrium, we say it's a quasi-static process. It's almost static. It's almost at rest. And I use the letter Q to abbreviate that. Now, if our system is also frictionless, then it should be true that if we take these pebbles off very slowly, one by one by one, okay, that our system will come back to its original state. That's only true if there's no friction here. Because if there's friction here, then you're going to be heating up the walls of the container, and some of your internal energy is going to be lost. But if there's no friction at all, then it should be reversible. Now, clearly, we're dealing with an idealization here, because frictionless doesn't ever happen. And quasi-static isn't very practical. It wouldn't make a very good car engine if everything had to happen quasi-statically. But, sort of like frictionless surfaces in elementary mechanics, these are useful idealizations that enable us to get, some first-order approximations. Now, of course, the laws of thermodynamics are true for all processes, not just the reversible and quasi-static ones. So the first law that we've written down here is always true. But to do the sort of calculations that we have been doing, we've been using the first law in its infinitesimal form, du is dq plus dw, and we've been integrating over paths in the PV plane. Again, that's only going to be true if pressure and volume are defined all the way along this curve. And that's only true if we're doing this quasi-statically and remaining very close to equilibrium. So this is always true. This form here, this differential form, and the analysis that we've been doing of these various processes, that is only true for our reversible and quasi-static. Now, another subtle point is in that differential form, when we write du is dq plus dw, strictly speaking, these d's aren't the same. Because you see, u is a function, so it makes sense to take du. It makes sense to find the change in a function. Just using standard differential operators, right? It's a differential. It's a very small change in a function. I should say a small change in a function. And that's a differential. So that's well defined mathematically. But dq isn't defined because q, strictly speaking, is not a function. So what dq mean is actually a little bit of either heat or work. So because, strictly speaking, this isn't a function, it's customary in many books to see not a real derivative d, but sort of a d with a bar over it, to say that, hey, this thing isn't really a state function. This just means a little bit of work, and this means a little bit of thermal energy. Okay. Now, we have already introduced a little vocabulary that shows us that sometimes this distinction between reversible and irreversible is important. That'll come up later when we're looking at how refrigerators work. And there are two names that we've already encountered that we'll use then when we're studying refrigerators. First of all, a reversible process in an insulated container. Well, because it's insulated, there's no flow of thermal energy. If that process is reversible, then we're dealing with an adiabatic change. But it is possible to have insulated processes, so there's no thermal energy, and yet have an irreversible process. This is called adiathermal. And it turns out that the expansion of a gas as it passes through a throttle valve in a refrigeration system is adiathermal, but it's not adiabatic. So it's an irreversible process. And that's important for our analysis later on. So that's one place where the sort of the definitions and the difference between a reversible and irreversible process will come up again. Now, what happens then? How do we go about irreversible processes? Well, again, the first law is still true. The second law of thermodynamics that we're going to see later is still true. And, the system's going to start at equilibrium, and maybe it's going to end at equilibrium, but there's going to be no line in between, right? But it turns out that for many functions, for any function, which is a state function, like internal energy, and then others that we'll define later on, like entropy, enthalpy, and then free energies, for all of those functions, they only depend on where you start and where you end up. So because they only depend on where you start and where you end up, if you wanted to say, find the change in internal energy between those 2 points, or the change in entropy, enthalpy, or free energy, you could use any reversible path, because any path will give you the correct change in a state function. So, for instance, you could use an isometric and an isobaric, and then you could find the heat flow using NCV/dt and NCP/dt, and you could find the work done using integral PDV, because now this is a reversible path, and those terms are well defined. Temperature is continually defined. Volume and pressure are continually defined along this reversible path. So any reversible path connecting the same points I and F could be used to find delta U, and later we'll use paths like this to find delta S and delta H. So reversible and quasi-static processes are certainly more complicated, but when we encounter them, we have the tools at our disposal to analyze them. Now let's look at one, a very important one, the free expansion of a gas. So this means that you have a gas in a container, but it's a two-part container, and one part's empty, i.e. it's a vacuum. All of a sudden you open the valve, and you allow the gas to expand through the hole, which it will. Let's just pretend for simplicity that both sides have the same volume. So the volume has doubled. Now, because there's going to be less atoms and molecules in this side, there'll be less collisions with the wall. The pressure is going to decrease. By how much? That depends on what sort of gas we're dealing with. We'll get into that shortly. So the volume certainly goes up and the pressure certainly goes down. Now, this is an irreversible process. Why? Because there's no way that you're going to, without using energy, get all of those gas molecules back in that other side. Now, you could do work and push a piston and get them all back over to the other side and then close the valve. But on their own, it's not going to happen. Because for any given molecule, there's a 50-50 chance of being on either side. So there's a 1/2 chance of that molecule going back to where it started. But when you have n molecules, the probability of all of them going back to that side is 1/2 to the n, just by the laws of probability. Now, if you have a mole, 1/2 to the sort of 1 with 23 zeros after it, that is vanishingly small. And so essentially it's 0. You could wait around for several lifetimes of the universe and you would likely never have it happen on its own. So because it's irreversible, we know that we're starting with, say, a pressure and a volume, and we know we're ending up with twice the volume and less pressure, but we can't draw a line there because pressure and volume are not well defined throughout that process. So exactly like we were talking about on the other side. We sort of know where we're starting, where we're ending up, but we have no idea about what's in between. So what can we say about this final state? Well, again, the first law is still true, but the gas isn't pushing anything. So it's not doing any work, and no work is being done on it. And if that were taking place with insulated walls, which we'll assume, then there's no heat flow into or out of the gas. So by the first law, the internal energy is a constant. Instead of writing it, I'll just highlight it here. The internal energy is thus a constant during the free expansion. Now, the first law is true for all gases, but from this point, there's sort of a bifurcation. We're going to consider two cases, either an ideal gas or a non-ideal gas. And both of these are very interesting and important examples. So first of all, what happens if it's actually an ideal gas? Well, we've said that U is constant, but we know that U depends on temperature only. So constant U would have to imply constant temperature. Or more precisely, because the internal energy is the same at those 2 points, the temperature must be the same at those 2 points as well. Now, if the temperature is the same, then from the ideal gas law, we can see that with temperature staying constant, pressure is inversely proportional to volume. Now, I shouldn't say it's being constant because along the way, temperature is not defined, but at the beginning and at the end, it's the same value. So I should be more careful with what I'm saying. Because the internal energy must be the same here and here, it's the temperature that must be the same here and here. And that means the pressure at this point and the pressure at this point are going to be inversely proportional to their volumes. Well, because the volume is doubled, the pressure must be half of what it was originally. So that makes a lot of sense, right? So this was V, this is 2V. We said this was pressure. This must be half of the pressure that we had to start with. That's where we end up. Now, unchanging temperature for the free expansion of an ideal gas makes a lot of sense, because if we look at, say, one molecule about to leave this side of the container, as it moves away from this other molecule, because they don't interact with each other in any way, the speed will stay constant. It's not going to change, because in an ideal gas we have non-interacting particles. So with constant speed, you have constant kinetic energy, you have constant internal energy, you have constant temperature. So because there are no intermolecular between molecules forces in a gas, there's no change in kinetic energy, internal energy, or temperature as a result of this expansion. So the temperature here is the same as the temperature after the expansion. So everything here is true for an ideal gas. Now, for a non-ideal gas, it's a little bit different. Let's call it, say, the free expansion of a real gas. Well, it's still true that the internal energy doesn't change. It's the same at the beginning and at the end. A real gas, PV, is not going to equal nRT anymore. There will be other equations, and we'll see some more complicated ones later in the course. But so we know that the volume is halved, but it isn't necessarily going to be true. Or sorry, the volume is doubled. It isn't necessarily going to be true that this point here is going to be at half the pressure. We can say something about our temperature at this point, though. For the ideal gas, remember, temperature initial equal temperature final. But with real gas molecules attracting each other very weakly, okay, because of that attraction, as they move farther apart, this is going to be slower because you have gained potential energy, okay, and therefore lost kinetic energy. You know, think of this like a rock separating from the Earth. The attraction of the Earth slows it down. So because of intermolecular attraction, this particle is now moving a bit more slowly. That's less kinetic energy. That's less temperature. This is now colder than it was. So in the free expansion of a real gas, it cools down. We can understand that by looking at a potential energy curve. And then this is a distance r. And there's sort of a potential well that, say, would describe the electric potential energy between these two particles. There's no potential energy at all for an ideal gas, but for real gases, they attract each other a little bit. So let's say the particles happen to be separated by this distance. Now, if you increase that separation distance a little bit, okay, then what happens is there's more potential energy, and therefore less kinetic energy. And therefore, it's colder. So right here, you have less potential energy, more potential energy than you did before, because we just climbed up the potential energy curve. That means they're going to be going a little more slowly. That means that gas is cooled off. Now, you may have noticed some pictures there that I haven't filled in, and we'll go back to those in a sec. So for real gases, the temperature changes when the gas expands. And that's just because, again, the particles attract each other a little bit, so you actually lose kinetic energy as they get further apart. Now, there's all kinds of really important applications of that. You may have noticed at camping when you use, say, compressed propane on your stove. those propane tanks get really cold. You will see later that this effect of cooling down as a gas expands is vital in explaining, understanding how heat pumps and air conditioners work. And we'll come back to that later in the course. So just to go back then, and to make another statement. I've said here the temperature changes when the gas expands. Most gases actually cool down. And that's the case that I've considered so far. So, propane cools down when it expands. Refrigerants cool down when they expand. But it turns out that there are some gases where the, say, initial concentration is so high, there's so many intermolecular collisions, then as the expansion occurs, the number of collisions actually goes down. And that means there's less interaction between the electron clouds than there was before. So in these gases, which are, say, more dense at standard temperature and pressure, an example of that would be like hydrogen, then this expansion, there's actually less PE due to the fewer collisions, and therefore more kinetic energy, and it's actually hotter than it was. So hydrogen actually heats up upon expansion. Now that means it's not very good as a refrigerant, but just to give you a comprehensive picture, the point is that real gases change in temperature. Most of them are here on the curve and will cool upon expansion, but some of them are over here, and so the particles are packed really close together. There's not very much separation between them. So when you give them a little bit more room, suddenly there's less potential energy because the electron clouds are not bumping into each other all the time. So they actually gain kinetic energy and get a little bit hotter. Not very many, but there are definitely gases like that. Some, like hydrogen and helium, actually warm up upon expansion. All right, so what we've done here is we've defined reversible and quasi-static processes and said that really we've been assuming all along through our analysis up to this point that we're dealing with the reversible and quasi-static process because we've been writing down things like this in its differential form, and that is only possible for a reversible and quasi-static processes. You can only draw a line in the PV plane if the pressure and volume are defined at every single point. And that must be, in order for that to be true, you've got to be going really slowly, making really slow changes, and it has to be frictionless. Now, non-RQ processes are still important in thermodynamics, and the laws of thermodynamics in their macroscopic form are still true, but you can't draw a line in the PV plane to analyze them. But for state functions in particular, that's not a problem because between any 2 points in the PV plane, so that's for reversible, this is for irreversible. For any 2 points in the PV plane for a state function, you can just connect them with any reversible line. More on that later in the course. And here's the activity that we're going to do in class. We're actually going to make a practical thermodynamic cycle. We're going to build an engine. So, but instructions and materials provided in class. For now, that's all we need to do for our pre-lecture video. And see you in class.